what we are looking at is the user interface of Turbo Design 1, which is the 3D inverse design code, and we will use it to design the impeller wheel for the CPU cooling fan. So for the baseline design, I have opened the impeller input file that was exported from the mainline code TDPre, and as you can see, all these specifications here like flow rate, RPM, etc. have already been filled in from the TDPre file. And we can also see the meridional shape, which again comes from the mainline code, along with this 2D grid, which is automatically created and can be adjusted using these options here. And the solver is actually a 3D code, and even though we don't have a numerical grid in the tangential or pitchwise direction, it solves the equations using discrete Fourier transforms, and that's why the code is very fast and is numerically quite efficient. Now, for thickness, we support different types of blade thicknesses, such as normal and tangential, and in terms of type, we have the simple constant thickness as well as more complex distributions like the Naka profile and flexible control points. But in this case, we can go with a flat plate type constant thickness, as typically seen in these types of fans. And actually, this possibility to specify thickness as part of the inverse design is very useful because it guarantees structural integrity. And then if you have some existing thickness profile, then you can also import that as well using an option here. And then we specify some fluid dynamic inputs, which is the blade loading. And this is actually the most important parameter for the inverse design method. And here we first specify the span-wise RVT star, which is the swirl distribution from hub to tip. And here 0 span-wise location is the hub and 1 is the tip. And we are imposing the span-wise swirl distribution at the leading edge and the trailing edge of the blade row. And the distribution is free vortex, so there is 0 swirl at the inlet, meaning a purely radial flow, and a constant value from hub to shroud at the outlet. And if you recall the Euler turbomachinery equation, the difference in RVT star between the inlet and the exit gives you the specific work of the blade row. And this is important because it means that every design coming out of TD1 respects your required duty point. And now that the overall blade work is fixed, we need to specify how it varies from the leading edge to the trailing edge at the hub and shroud sections. And for this we have the stream-wise blade loading, which directly controls the pressure jump across the blade. And here we have a parabolic section from the leading edge to a point here that you can vary, a linear section between these 2 points, and from this point to the trailing edge we have another parabolic section. And the loading at this point defines the incidence at the leading edge, and at the trailing edge the loading is always 0, which satisfies the kata condition. And so with these 4 settings you can easily parameterize the 3D blade loading for manual adjustment or for automatic optimization. And of course the distribution is mid-loaded for this baseline impeller. Now, even though the program is fully 3D, it runs very quickly. And just within 5 seconds or so, and it gives you the blade geometry and also quite an accurate inviscid flow information. And this information is something that we can use to iterate on the design. So we can first take a look at the converged impeller geometry using this 3D plot here. And then we can create 2D plots of, let's say, surface pressure at the hub and shroud. And we can also relate the isentropic Mach numbers and isentropic velocities to some performance parameters that we can use to explore the design space. And you can see these performance parameters here in the project manager window. Such as the indicators of diffusion and profile loss, and geometry parameters such as throat area. And then under this UDP section, you can also use Python scripts to develop your own specific parameters. And finally, the impeller design can be verified with a CFD or FEA analysis. And for this, the geometry can be directly exported from Turbo Design 1 to different format files that are needed for mesh generation, such as curve files for TurboGrid or step files for ANSYS Mechanical.